Today we'll be looking at Lesson 3.04, Water Wonderland. Today's objective is I can use an equation to model and interpret a function in 2 out of 2 problems. We're going to be looking at equations today. So here's a story about a water park. Allie and Dane both work at a water park, and at the end of each month they have to drain and clean the pools for their rides. Now their pools are different sizes and they use different water pumps on them to empty them. So we have a graph here that shows the amount of water in each of the pools while they're draining. You can see Allie's pool is in red here. It's listed as A of X for Allie. And you can see it decreases that way. We are draining the pool, so it starts at a certain level. This is gallons of water. And it goes down until it hits 0 gallons at some time. Dane's pool is represented by D of X, or the blue line, and it looks like that. Now, even though we don't have any numbers on these graphs, we can make some interpretations about the graph still. So looking at this graph, can we tell which pool is bigger? Well, at the beginning, both pools are full. So if we look at the y-intercepts and we compare them, we can see that Allie's has a larger amount of water. So Allie's pool is bigger, and that's because the y-intercept is bigger. Now, which water pump is faster? Which one is draining the pool at a higher rate? How can we tell the rate of change? The rate of change on a linear graph, which is what these are, right? These look like straight lines. The rate of change is what we know as the slope. The steeper the slope, the faster it's changing. So which one of these has a steeper slope? The red one does. This one is going down faster. So once again, Allie's pump is faster, and that's because the slope is steeper. Now this last question, which pool takes longer to drain? How can we tell that? Well, now if we look down here at the x-axis where it crosses, where both of them hit 0, we can tell when those pools are fully drained. So this one hits it at this point in time, this many minutes, and this one takes some amount of time longer, some minutes more. So Dane's pool takes longer to drain, and we can tell that because the x-intercept is larger. So Dane's pool takes longer to drain, and that's because the x-intercept is bigger. So we've talked about these features of functions, the y-intercept, the slope, the x-intercept, but you can see that when we have a story, when we have a context, those features actually mean something. The y-intercept in this case is the amount of water in the pool initially. It's the size of the pool. The slope is how fast it's draining, how fast the water pump is working. And the x-intercept is the time it takes to fully drain the pool. So now we're going to try to find an equation. It says Dane found that the pump he uses drains water at a rate of 1,000 gallons per minute. That is so much water, 1,000 gallons. Wow. It takes him 24 minutes. His pool drains in 24 minutes. So it takes 24 full minutes to get down to 0. And we're going to write an equation to model d of x. Well, let's think about what this equation might look like. We're going to have d of x equals something. And we did see that this is a straight line, right? So what equation do we use to model a straight line? We have a form for it, a linear equation. This is going to be mx plus b, good old slope-intercept form. And we have m and b that we need to fill in. So then we ask ourselves, did they give us either of these terms in the problem? It says, we have 1,000 gallons per minute and we have 24 minutes. Do either of these values correspond to either the slope, the rate of change, or the y-intercept? We said the y-intercept was the gallons of water in the pool, right? The y-intercept is how big the pool is. So did they give us either of those things? Well, we don't have one that says gallons. We don't have a size of the pool, but we do have a gallons per minute. That sounds like a rate. That is our slope. 1,000 is our rate. And then notice that we are draining the water. We're not adding water, so our slope is going to be negative. We're removing 1,000 gallons per minute, so our slope is negative. But they didn't give us our y-intercept. We need to figure that out on our own. So we need to figure out how many gallons there are in the pool. Is there a way we can use this rate and this number of minutes to find the total gallons in the pool? Well, let's see what happens if we just multiply them together. We have 1,000 gallons per minute, and I'm going to take my units with me, and I'm going to multiply by 24 minutes. Our minutes units will cancel, and we get 24,000 gallons. Oh, good. Well, that's the right units. We needed gallons to be the size of the pool. And does this make sense? Let's do a sanity check. 1,000 gallons per minute, 24 minutes, so at 1 minute it would have drained 1,000, at 2 minutes 2,000, at 3 minutes 3,000, and so on. So after 24 minutes it drains 24,000 gallons and it's empty at that point. So yeah, it totally makes sense that 24 gallons would be the size of the pool we started with. B is 24,000. So we put that all together and we get this equation. D of x equals negative 1,000x plus 24,000. And it asks us, what does each part of the equation represent? What does this number represent and what does this number represent? Well, we said negative 1,000 was the rate of change, right? The rate at which we were draining the pool. What was 24,000? 24,000 gallons. We said that was the size of the pool. That's the amount of water we started with. So given that info, where can we label the graph with these numbers? Let's see, we said d of x was negative 1,000 x plus 24,000 gallons to start with. And we also know that it drained in 24 minutes. So we know that it was drained here, so this must be 24 minutes. And we also know this is where it started. We said this is how much was in there when it started, so this must be 24,000. And we know that this is the slope. So we could say the slope of this blue line is negative 1,000. We could even figure out what this one is, what this number is right here, because these are marked. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 markings, and we got up to 24. So each of these must be 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So Allie's pool must take 20 minutes to drain. So what is the domain of d of x? What does the domain here mean? Well, let's see, we started at 0. Remember, our domain is going to be our input values, our x values. We're going to look at this function right here, this blue one, d of x, and see where it exists on the x-axis. Looks like we start here, right at 0, and it exists continuously, keeps going, all the way down to 24. So I'm just going to I'm going to color a little line there, and at 24, it's empty. So if we think of this as an interval, like a number line, we start at 0, we end at 24. So we write that like this, 0, 24, and then we decide whether we included those ends or not. There was an amount at time 0, so that is a point, that is included, there's a point, closed dot there. And then at 24 minutes, the gallons were 0. There were 0 gallons in the pool. So that's also a dot we measured. So that is also a closed dot. Since they're both closed dots, we do square brackets. Remember, we use round brackets when we don't include the endpoints. And we use square brackets when the endpoints are included. Since both of these are included, we use square brackets. Now, what is the range? I'm going to do a range in a different color, maybe pink. What's the range here? Ranges are y values. Where does this blue function exist on the y-axis? Well, let's see. It starts up here, and it's going down, 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 down. So just follow it down, 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 down. Goes all the way down to 0. And then we have a closed dot at 0. So what is this interval? It looks like we're going from 0 at the bottom to 24,000 at the top. So our lower bound is 0. Our upper bound is 24,000. And once again, we have closed dots, so we're going to do square brackets. So what do those things even mean? Domain and range here. What does that even mean? 0 to 24. 0 to 24. Well, it's 0 to 24 minutes, and we're draining the pool. So this is the full time it took to drain the pool. And what about 0 to 24,000? What does that mean? Well, this is the y-axis. This is the amount of water in gallons. So this is how much water was in the pool during that time. So it's the amounts of water as the pool drained. $24,000, and we started draining it, and it went down and down and down and down and down until it got to 0. So the domain and range also have physical interpretations in this story. Okay, so Allie's pool holds 28,000 gallons, and it takes her 20 minutes to drain it. We need to write an equation for her pool's amount of water now. So we're going to start with a of x again. We said this is a linear equation, right? So we use the same format, mx plus b. We need an m and we need a b. And we ask ourselves again, did they give us either of these things? Well, let's look. We have 28,000 gallons and we have 20 minutes. Well, neither of those things sounds like a rate. Rate would be gallons per minute, probably. So we don't have our slope. But what about b, our y-intercept? We said our y-intercept was how large the pool was. This pool holds 28,000 gallons. Oh, so they did give us b already. We have 28,000. Our y-intercept is 28,000. So now we just need to figure out the rate. We need a gallons per minute. Well, if we need gallons per minute, maybe we just take gallons, the number of gallons divided by the number of minutes, and see what we get. 28,000 gallons divided by 20 minutes, we get, I believe, 1,400, if you put that in your calculator, 1,400 gallons per minute. That's the right units for a rate of change, gallons per minute. So 1,400 is going to be our slope. And we also need to remember we're draining again. We are draining the pool. So this is negative 28,000 gallons. We are losing 28,000 gallons over the period of time, so this is going to be a negative slope. We also know that by looking at the graph, we can see that slope goes down. Both of these slopes go down, so we'd expect it to be a negative slope. So overall, let's finish up writing this equation. We just substitute in m and b now, 1,400 x plus 28,000. So that is our equation for Allie's pool. So now that we have equations for both of them, we can compare them. For instance, when does a of x equal d of x, and what does that mean? Well, they're going to equal when they meet. Looks like it's that point right there. So if we follow that down, you can see that's at 10 minutes. If we look at the amount of water, that's on our y-axis, that's 14,000. So it's 10,000, 12, 14, 16, 18, and 20,000. So this is the point, oh, that is a terrible color for this. Let's use white. 10, 14,000 is the point where they intersect, or we could say it happens at 10 minutes. And what does that mean? What does that mean in terms of the physical world? Well, we know at 10 minutes, both of these functions have 14,000 gallons. So it means they have the same amount of water in each pool. At 10 minutes. So that's where both pools have equal amounts of water. Let's skip a couple of these, but let's stop on this one. When is a of x greater than d of x? Can you see that on this graph? Well, sure you can. A of x is above d of x here, so that's where it's greater. We can just circle that right up here. A of x is greater than d of x in this region right here. If we wanted to say that was during a particular time, we could come down here to the x-axis and say, well, it's from 0 over to where they meet, which is 10. And everything in between. That's where a of x is larger than d of x. So if we wrote that as an interval, we'd say that's from 0 to 10. Oh, maybe a round bracket instead of a square bracket, since they're equal at 10. We could also say that's 0 to 10 minutes. That's another way of saying that. So at the beginning, all the way up to 10 minutes, Allie's pool has more water. And then after that, Allie's pool has less water. You can see that on the graph. Allie's function is below Dane's function. So this means Allie's pool has more water for the first 10 minutes. Cool, so we can compare functions, especially once we have equations, to figure out certain information about them. All right, and now we have yet another thing we can do, which is adding functions together. So this month, Allie and Dane decided to work together by putting both pumps in one pool at the same time. So they're going to empty one pool first and then move both pumps over to the other pool and empty that one. And they came up with this equation right here. G of x equals a of x plus d of x. Remember, a of x is, let's get a color we can actually see, maybe pink. Here we go. A is how much water Allie's pool has. Water in Allie's pool. And d of x is the water in Dane's pool. So now if we add those both together, how would we describe that? It's not a trick question. It's actually, it's so simple it almost feels obvious. What would we say if we added the water in Allie's pool to the water in Dane's pool? What would that be? Well, it's the total water in both pools. We just added the water in Allie's pool to the water in Dane's pool, and we get an amount that is both pools combined. So it turns out we can actually just add them exactly like we think we ought to be able to. And we can get a new function out of it. So let's look how this works. Oops. Let's go back down here. So g of x equals, I'm just going to take this function and I'm going to write it out. This is a of x, negative 1400x plus 28,000. And now I'm going to add d of x. Once again, just write it out exactly like it says. Now I'm going to write it on the next line, and I'll show you why that is. If I write it on the next line like this, then we already have our like terms grouped. We have our x term, and we have our units term. And we can add those straight down. So negative 1400x plus negative 1000x will be negative 2400x. And 28,000 plus 24,000 will be 52,000. And that is our new function, g of x. g of x equals negative 2400x plus 52,000. And just like we did before, we can interpret these terms. This is our rate of change. So negative 2400 gallons per minute is our rate of change for both of those pumps together. And then 52,000 is the volume of both pools together. So if we take this new function out, we can actually graph it because it's just another line, right? This is the equation of a line, negative 2400x plus 52,000. And we can put it on the same axes as we had before, right there. And this is what it looked like. So you can tell if they work together, they will save some time. They won't have to wait for Dane's pool to finish. They finish in less time if they work together. Let's examine the y-intercepts really quick. So over here we have the y-intercepts. Remember we said this is the amount of water in the pool at the very beginning. And we have this question over here, true or false? If we add a and d together, these initial values, do we get the value of g? We said a was 28,000, right? 28,000 gallons, and d was 24,000 gallons. And the question is, do we get 52,000? Because that's what these two added together equals. Is that what's on this graph? Well, look at this point right here. 50,000, 52,000. Yeah, that did. That worked out. That is true. We literally add these two values together and we get the value on this line. So what does this mean in context? Well, this means that the initial values of the pools, when we add the size of Allie's and Dane's pool, we get the size of both pools combined. Now, can we generalize that to any time? Is that true at 15 minutes as well? Can we add this point and get this one up here? Well, let's look and see if it works. We can find out what these numbers are, right? So these are each 2,000, 2,000, 4,000, 6,000. Looks like it's right in the middle. So this must be 7,000. And then this one is 2,000, 4,000, 6,000, 8,000, again right in the middle, so this must be 9,000. So A of 15 is 7,000, D of 15 is 9,000, and if we add those together, we get 16,000. Well, let's look at the value on the green one. Let's see, this is 10,000, 12,000, 14,000, 16,000. Yeah, it did work. So it turns out we can take any two values at the same time, add them together, and we get the value in the new function. It doesn't matter what time it is. So we have literally added these two functions together over this whole interval, and we've come up with this new function. So that is everything for today's objective. I can use an equation to model and interpret a function in 2 out of 2 problems.